Hello everyone, today we discuss exponential functions. We already know about functions where x is in the base and a number or constant is in the exponent, such as y equals x squared. And in terms of exponents, x to the second is the same as x to the 1 plus 1. But here x is the base and 2 is in the exponent. How about 2 raised to the x? Is that the same as x squared? No, that definitely is not the same. Notice here that 2 is in the base and x is in the exponent. A function with a variable in the exponent and a constant in the base is called an exponential function. A simple exponential function can be written y equals a to the x, where a is a base and a is greater than 0, because if a was 0, and that's just y equals 0. If a was negative, then the functions could be really bizarre, or so it would not even be functions. And a is not equals 1, again, similar to when y is equal to 0, we will just be left with y equals 1. Let's talk about sketching the graphs of exponential functions. Let's look at a couple of them. F of x is equal to 2 to the x. As usual, when we're sketching curves, we find values for x and then plug in the function to find values of y. In this case, f of x is 2 to the x, so we have negative 2 1/4, negative 1, 2 to the negative 1 is 1/2, 0, 2 to the 0 is equal to 1, and 1, 2 to the 1 equals 2, and 2 to the second power equals 4. Now we plot these as coordinate points in red right here. We do the same thing for g of x is equal to 3 to the x, and h of x is equal to 4 to the x, so we're going to draw a curve through, let's say a red curve through these red dots for 2 to the x, and then a blue curve through these blue dots for 3 to the x, and then a green curve, little green dots for 4 to the x. There's a couple of things that we should be noticing right now is that from the left, all the curves are tending to 0, but they never go beyond y equals 0 line, or they'll never go below the x-axis, so there's an asymptote at y equals 0. All the curves pass through the point 0, 1, so there's the y-intercept at 0, 1 for all the curves, and all the curves rise as we go from left to right. Now let us sketch another set of exponential functions. F of x is equal to 1/2 to the x, g of x is equal to 1/3 to the x, and h of x equals 1/4 to the x. Now for f of x equals 1/2 to the x, we will plot them in red, and the points are here, similar to what we're doing with 2 to the x, 3 to the x, and 4 to the x. For g of x equals 1/3 x, you plot the points in blue, draw a smooth curve through them, or as smooth as possible. Let's do it. There goes your curve. That's 1/3 to the x. And thirdly, 1/4 of the x. Have them in green dots. Notice you're falling from left to right, going through 0, 1 as your intercept, and they are falling, and they're going down to the x-axis, but the x-axis acts as an asymptote. So these are the things that we notice. Now we're going to put them all together. Properties of f of x is equal to a to the x. And first of all, the graph of f of x will always contain the point 0, 1, regardless of the value of a. So if it is only a to the x, then the x asymptote, the y-intercept, sorry, will be at 1. 2 for every possible of a to the x is greater than 0, and note a to the x is not equal to 0, right? And if 0 is less than a less than 1, or if a is between 0 and 1, not inclusive, the graph of a to the x will decrease as we move from left to right. So it's decreasing if a is between 0 and 1, and if a is greater than 1, the graph of a to the x will increase as we move from left to right. Also mention that the asymptote will be the x-axis. Now, more elaborate ways of expressing exponential functions. Suppose we had another constant times the exponential function a to the x, such as y equals b a to the x. Here b is your y-intercept, okay? So that will shift the intercept up from 0, 1 to whatever number b is, right? A more elaborate form is y is equal to b times a to the x plus k. Here k will be your y asymptote. So whatever k is, whatever you shift it up, remember that originally it was at 0, but if you add a plus k, that will be your new asymptote. Let's talk about shifts in the coordinate plane of exponential functions. Now, if we have, let's say for example, f of x is equal to 2 to the x, and we graphed that earlier, so it looks like this green curve right here, and we wanted the graph f of x is equal to 2 to the x minus 3. Recall what we knew from shifts in functions, general functions previously, that if you had an x minus 3 somewhere, like in a parentheses, then that would have been a shift to the right. The same thing happens to the exponential functions. If we look at it at the table, notice that the numbers here, 1, 2, 4, are repeating further out to the right on the x-axis, 1, 2, 4. Okay, so x minus 3 will shift our original graph 3 units to the right. So this is a shift 3 units to the right. And the similar thing will follow for other shifts. In just the same way that we did our other shifts previously, a similar thing will happen. Now, let's talk about exponential functions being one-to-one functions. Exponential functions are always one-to-one functions. If you notice the curves that we drew before, they were all one-to-one. In that on a graph, they will pass both the horizontal line test and vertical line test if you just want to look at it graphically. What that means is if we have a to the x being equal to a to the c, or if a to the x intersects a to the c, then x will be equal to c at that point, or x is equal to c if a to the x is equal to a to the c. Now, example here of a question, find x at the point, so find the x at a point where f of x equals g of x, or where f of x and g of x intersect. So f of x is equal to 4x, 4 to the x, and g of x is equal to 4 to the 2x plus 1, right? So again, like a to the x equals a to the c, so we set a equals c, or x equals c. So here we set x, since they're the same base, right? Same base, 4. You can set the exponents equal to each other. So x will be equal to 2x plus 1. And then we're trying to solve for x, so we could, let's say, subtract 2x both sides. And so negative x will be equal to 1. So x will be equal to negative 1. And so we've solved for x. You can plug in x equals negative 1 So 4 times negative 1 is equal to 4 times 2 times negative 1 plus 1. That's negative 2 plus 1, which would be equal to negative 1. So that solved and checked. Okay? So that is one of the ways that we can solve the intersection of exponential functions. Okay? Let's talk next about graphing the function e to the x. Now, e to the x is called the natural exponential function. Natural is a special exponential function called the natural exponential function. And this number e occurs in several ways in our daily activities and in a lot of the math that we will do later on. Okay. Here is a way that we could develop the number e from 1 plus 1 over x to x, and that is looking at an approximation for e, and e is approximately 2.718281828 and so on as x tends to infinity from the 1 plus 1 over x to the x. But this is what we need to kind of remember, that e is approximately 2.718. And so we want to graph the exponential function, or the natural exponential function f of x is equal to e to the x. So let us plot these at x and e to the x. So 0 is 1. 1 goes to e, which is 2.718, and so on. And so your graph of your natural exponential function will look just like a regular exponential function, except that 1 maps to e and 2 maps e squared, and so on and so forth. Okay, let's talk real quick about compound interest. We're compounding interest over time. Here we're developing a formula. A is equal to p times 1 plus r to the over n to the nt. Now, A is the current balance, or some books might say remaining balance. P is the initial deposit or initial amount. N is the number of compounding periods in a year. So if it's compounded monthly, it's 12. N will be equal to 12. If it's compounded half yearly, then N will be equal to 2, and so on. T is the number of years. And there's something else that is very important. R is the annual rate of interest, but it's always expressed as decimals. R is always expressed as decimals. So let's look at a real quick example. We have our formula here. A is equal to P, and 1 plus R over N to the NT. And we have to calculate the balance for $100. So that is our P at a 5% rate, express a decimal, that's 0.05. And then for 3 months, and then you have to describe the 3 months in terms of years. Okay, so we have to describe the 3 months in terms of years. So A now will be equal to 100 and 1 plus 0.05 over 12, and then times 12, which is n again, and then times 0.25, that's the 3 months in terms of a year, that's 1/4 of a year, and the rest is just calculator work. You plug this into your calculator and you should get 101.26, 101.26, and so that is your answer, and you're done.